So we're going to do lesson 8, or unit 8, lesson 2, rather. This is actually the first lesson in this unit, believe it or not. We do the introductory one just to get you used to working with the nuts and bolts and review some of the algebra skills. On the right-hand side, again, are the basic definitions we covered yesterday, along with the Pythagorean identities. All of those will need to be memorized, or at least be able to be generated. All right, so you have a note card to work with them now for ease, but you're going to have to start to pull them from memory before the test because you're not going to have your note card. So in this section, let's talk about the directions. So the directions for all of the problems in the first half are to verify. Do you know what the word verify means in math? Verify means, yes. See if it's correct. Basically, is the equation true or false? As we move into this section, I'm going to tell you all of the equations I'm going to give you will be true. But you have to prove it, and you have to prove it using legal algebra, not math magic. Right? So you have to show every step, which should be your thought process, and the logic of it. So if I ask you to verify in the first one, what I would suggest doing is starting on one side. Let's start on the left and apply PEMDAS. Okay? So I'm going to draw a little wall in here. I'm going to work on the left-hand side. What do I do first for PEMDAS? Parentheses all the way on the inside, so this becomes 2 plus 1, which is 3. Then what? Exponents, 3 to the third. What is 3 to the third power? 27. So now I'm here, 2 times 27, 6 minus 2 times 27 is? Negative 54. 6 minus 54? Negative 48. So notice that one of the strategies, and I did this on purpose with color, was to start on one side, work your way through. Do not even look at the other side right now. Now we can come back and look on the other side. What is negative 4 times 12? Negative 48. Notice these two things are equal. They should come out to be equal, but this is where the logic, the application of PEMDAS, following algebra rules, is clearly shown. What you did to arrive at this answer. So it would not be appropriate to write negative 48 equals negative 48. That's not going to give you the credit. If we look at the next example and we follow the same thing, we draw on the wall. Let's start on the left side. What do I need to do on the left side? Nope. We don't have to factor. Nope. Haven't ready yet. Take a group and add 16. That's just combining like terms. Yes. On the left. So on the left, I combine like terms, x squared plus 6x plus what? 9. Then I can move to the right side now, shift my focus, don't worry about what's on the left, and I can actually multiply all this out. X plus 3 times x plus 3, which is x squared plus 6x plus 9. Are these the same thing? Yes. So I've verified that they are the same. The only time prior to this that you have seen verifying identities or verifying equations was when you remember doing linear equations and they would come out to something like 6 is equal to 6 because all the x's would cancel, and you would say that's a true statement. Yes, and the answer would be all reals. So like above it you would have something like x plus 6 is equal to x plus 1 plus 5. And you would say, oh, I would solve, subtract x from both sides, 6 equals 6, that's true, it's all reals. This is an application of verifying identities, that the equation you have on the right is the same one as that you have on the left. Therefore, any value of x would work. That's what's true here. Any value of x would work if you plugged it in to the original. Any value, well, everything's already plugged in here for you. Okay, this is where all of that ties together with things that we've done before. Now we're going to do it combined with what we did yesterday. So, first thing I'm going to do here is I'm going to give you a bunch of directions. I want you to copy them down. Erase this. You can paraphrase. That's fine. I would say the most important one is number 5, try something. All right, number 1, we're going to work with one side of the equation at a time. It's better to pick the more complex side because then you're simplifying it. You're making it smaller to match the smaller other side. Look for opportunities to factor, add fractions, square a binomial. So that's what we just did in the warm-up. Create a denominator, an LCD. See if fundamental identities, such as Pythagorean identities, will help you simplify it at all. If everything else doesn't work, the very last step we would suggest to you is to take everything into sines and cosines. Okay? So when you read through, you don't have to write this verbatim. Read it, think about it, paraphrase it. These are your steps for this entire section. All right, so 4 examples for today, and they're going to start out right from the beginning with difficult ones. We're going to jump right into the deep end. So if we take a look at example 1, if I had a black marker, it worked. Example 1 is going to be cosecant of x. All right. Obviously, the right side is as simple as you can get. Side of x. So I wouldn't even touch the right side of this. I would start on the left side. Couple things to notice about the left side. Do I have anything that says sine? No. Okay? So the fact that I don't have sine over there, that's one indicator. Second thing I'm going to ask you, do you have anything that has squareds in it that look like a Pythagorean identity right now? There are no squareds. So I say that because some students see 1 minus cosine and think, well, if I rearrange this first one, I can get 1 minus cosine. You can't. You get 1 minus cosine squared. That's not going to help you. All right, so right from the beginning, we can eliminate Pythagorean identities as our intro choice. So I'm going to start on the left side. Based on what you did yesterday, what do you think would be a good strategy? You want to go to all sines and cosines? All right, that would actually be a good idea here because the answer we're looking for is just going to be in terms of sine, and since everything here is not in sine, converting would be very helpful. So step 1 would be to take 1 over sine x plus cosine x over sine x times 1 minus cosine x. Okay. Now, when I have 2 parentheses right next to each other, what operation does that indicate normally? Multiplication, or your favorite 4-letter F word? FOIL? Correct? So if I FOIL this, I'm going to get 1. I'm going to write all of this out. Some of you won't have to do this moving forward, and you probably can't see it because this marker's dying also. So switch to purple. We're going to get 1 over sine x times 1 plus 1 over sine x times cosine x. This should be a minus sign. This times this, this times this. Then I'm going to go to my middle, plus cosine x sine x times 1 minus cosine x sine x times cosine x. Are there any questions about the purple FOIL line? We're all good? All right, now if I do another line of work here and I multiply all this, this ends up being over 1, so I get 1 over sine x minus cosine x over sine x plus cosine x over sine x minus cosine squared x over sine x. What cancels? That's going to make my life so much easier. This is not by accident that this happens. The middles are going to cancel. These are opposite terms. What do you notice about the first and the last term in terms of the denominator? They're both sine. So that means that I can, since you can add and subtract things with like denominators, I can put them together in one fraction. Notice I did not make it sine squared. When you add with like denominators, the denominator remains the same. All right, now, this is where the directions, when you read them literally that we wrote down earlier, might seem a little tricky to you. As much as we're not focused on this right side, it's going to give us a hint as to where we need to go. Everything needs to be in terms of sine, which means my numerator can't have cosine squared in it. But the fact that there's a cosine squared should make you think about what on the right side of the board. What's over here that's going to help us with squares? The first one. What can I rearrange this first equation to say? I can say sine squared is equal to 1 minus cosine squared, correct? So if that's the case, what can I replace this with? Sine squared x, all of which is over sine x. And now you just might get a little excited because we're almost there. What cancels? One of the sines, right? This is gone and now that's gone. So it leaves me with just sine of x, which is exactly what I needed here. Because sine squared is the same thing as sine x times sine x divided by sine x. Right, so I just did it in short form. Now, here's my declaration to you. All of these are true statements. Algebraically, both sides are the same thing. They look different. You legally need to be able to get there, so there's no mistake. These are correct. We've been using the same problems for 12 years. They have been vetted. There's no typos. You should be good to go with this. So as you're working through, these are set up like little math puzzles that will work out. The joy is in getting them to work out. And now you can see why math people love this. Maybe. All right, let's try number 2. Here we go, number 2. Let's go all purple, I think. Number 2, cotangent squared x over 1 plus cosecant x is equal to cosecant x minus 1. All right. Now, I remember adding this one to the notes once upon a time because there are some of you that are very good at equation solving, and you see this as a proportion that you can cross multiply. The problem with cross multiplying is that you are working both sides at the same time, which is illegal. You have to simplify one side, simplify the other. Okay? So my suggestion to you is, which of these is the more complicated side, the left or the right? Left. Okay, so let's focus on this left side to start with. If I look on the right, everything is in terms of cosecant. Over here, the bottom's in cosecant, but the top is not. Okay? This would be what I would hope your thought process would be. I have a cosecant. That cotangent needs to go, but it's cotangent squared. Is there anything on the board on the right that involves squares that relates to cosecant? Second one. What is cotangent squared known as? Close, close, close. Cotangent squared is known as cosecant squared minus 1. All right, well, if I choose that Pythagorean identity kind of alternate route, that's now going to get me all in cosecants in ones, which probably is going to get me closer to where I want to be. So up top here, I'm going to try that. I'm going to try cosecant squared x minus 1, all of which is over 1 plus cosecant x. Now, if your brains are kind of starting to dial into the process, what is cosecant squared minus 1? How can I break that down? That is a what? We did this in the examples yesterday. It's the special case of factoring of difference of squares. Yes? So if I take the top, I can factor it into cosecant x minus 1, cosecant x plus 1, all of which is over 1 plus cosecant x. Oh, that looks pretty good. Why did that help me? Right, and didn't I end up where I needed to be over here? As much as we're not touching the right side of these identities, they give you hints about where to go and how to get there. And that's what we need to start connecting and strengthening. So notice now I have this is equal to this. My identity is done, yes. Right here. I took this purple, which is an established identity, and I rearranged it to isolate cotangent. In doing so, I got everything in terms of cosecants and ones. Okay. So I will tell you, this strategy of using a Pythagorean identity to get to difference of squares that factors will come up a lot. Yes, sir?
Couldn't you just divide the orange part out to equal cosecant x minus 1? Couldn't you just, divide it? You didn't have to factor.
Okay, so explain to me what you mean by divide.
You could do, the cosecant x cancels with the cosecant squared x to just equal 1.
Oh, gosh.
You can't do that?
That breaks my heart. Here's the reason why. It's a good question, though, because it's going to come up a lot. This is, sometimes I'll write, a cute note that says math magic, question mark. Of course, I have no other marker colors but green and purple in here. How about lime? Go with lime. Orange. Can I reduce the 6 and the 3? Same idea, just that now we're dealing with cosecants. Okay, everybody see why I wrote the green the way I did to answer his question? You can't cancel across adding and subtracting signs. If this was cosecant squared x times 1, 1 times cosecant, then you can. Multiplication, yes. Adding and subtracting of terms, no. Yep, good. Okay, done. Next one. Number 3. Oh, gotta love number 3. Tangent of t plus cosine of t divided by sine of t. This looks like fun. Is equal to secant of t plus cotangent of t. I think we just ramped up 5 of the 6 in one problem. All right, before you do anything, those of you that are starting to understand the direction where the problems are going, I would bet in your head right now you can hear me saying the following that I said before. If you don't have something that's in common, go to all what? Sines and cosines. Yes? If you don't have something in common, notice I've got 5 different ones, go to all sines and cosines. I'm going to tell you in this problem, that is not the best strategy, and here's the reason why. Do you agree this left side is the more complicated side, this side? If you go to all sines and cosines, aren't you going to end up with complex fractions? Fraction, fraction over fraction? Yes? Okay, so let's talk about another algebra strategy that you may not use that frequently, and it's over here. It's called splitting the fraction. Right? If you have this scenario of a fraction with one term in the denominator, just the sine x, you can split the fraction into 2 separate ones. So basically, it's kind of like if you look at the last example, we're going in the other direction. We're taking one fraction, we're splitting it into 2. So in this example here, I can turn this into sine of x over sine of x plus 1 over sine x. Do you notice how doing that I got rid of my denominators when I apply the definitions at the top? This becomes 1 plus cosecant x. And now I have no more denominators. It's a strategy called splitting the fraction. We're going to use that here. We're going to split the fraction. Split the fraction. Okay. So I'm going to write this as tangent of t over sine t plus cosine t over sine t is equal to what's on the right. Now, is there anything that I just wrote that matches perfectly left and right? They are the same thing? Yeah. Yeah, is it cosine t over sine t the same thing as cotangent t? Okay, so we are almost there, which means this is the only thing we have to clean up yet. This is the time when it would be appropriate now to go to our sines and cosines. So what is the definition of tangent? Sine t over cosine t, correct? Sine t over cosine t. So here's what I have. I have sine t, notice I changed colors, over cosine t, times what? 1 over sine t, cancels, cancels. What's 1 over cosine t? 1 over cosine is secant t plus cotangent t. And I'm done. Way, way better than all of the work if you went to all sines and cosines from the beginning. Yes. What's 1 over cosine? Because I canceled the signs. All right, so we also have that prerequisite skill of taking a denominator, multiplying by its reciprocal. That's back, kind of all playing into this. What questions do you have? We only have one more example. A over B divided by C. Just don't worry about the trig right now. Let's just talk about pure letters. What's the denominator technically here? C over what? C over 1. And the rule is if you have a fraction divided by a fraction, multiply by the reciprocal. The only difference is I don't have a plain variable, I have a trig term. Okay? So that's that bridge that we're kind of climbing to, trying to get over. Anybody else? All right, let's do the last one. Deep breath. Woo. Stress reliever. All right. I would think number 4 is probably one of the hardest, not the hardest ones that, I mean, it's the hardest one you've seen so far, but your test isn't going to be much more difficult than number 4. So if you're with me through this and it kind of makes sense and you think you can do it, you're right on par. Right? So when you see these, yes, there are some that are much more complicated. I'm not going to be assessing you at the much more complicated level. Right, this really puts together everything we've done this year. It's got rationals, it's got LCD, it's got trig functions, it's got definitions and substitution, all of that. So if we're good little problem solvers here, here's my suggestion for you. We agree that this left side is much more complicated, right? Okay, one thing to keep in the back of your mind is cosecant's other definition is what? 1 over sine, right? So anytime I have a sine in the denominator, that's a good thing. So like this is a good thing for me. This means I'm on the right track. What's really screwing me up is going to be this over here, right? This 1 plus cosine is not. I cannot split the fraction here. The reason I can't split the fraction is because this is an expression with a quantity. It is not one term. So splitting the fraction is not appropriate, which means we're going to have to do LCD. What's the LCD? This times this, correct? So what do I need to multiply my first fraction by? Sine. So I'm going to multiply this by sine theta and this by sine theta. What do I need to multiply the second fraction by? 1 plus cosine theta. So this is going to be 1 plus cosine theta. And this is going to be 1 plus cosine theta. Okay. Now, this is where those of you who start to struggle with these problems, you forget to look ahead at where we're going. And here's what I mean by that. If I look over here, I want 1 over sine. If I distribute this sine in the bottom, isn't that going to give me a more complicated denominator than what I really need in the end? Are you with me? If I take this and multiply sine times 1 and sine times cosine, it's going to blow up my denominator, which isn't going to help me because ultimately I just need it to be a plain old sine. So this is where, to help you out, I would suggest leaving my denominator as sine theta times 1 plus cosine theta. What am I ultimately going to have to get rid of out of that denominator? The 1 plus cosine. We're right now trying to manipulate the numerator to get what we need. So let's see what we have up top. If I multiply this, I get sine squared theta plus cosine theta plus cosine squared theta. Now, let's see here. I'm going to call on one particular person, see if he remembers. Reeves, do you remember what we did in the example when you came up? Right. In one of the problems that you did in your homework, the only way to do the problem was to rearrange your three terms, your A, B, C terms, and substitute a Pythagorean identity. So here's what I mean by that. If I turn this into sine squared theta plus cosine squared theta plus cosine theta, what does this numerator right here, what can I replace just those two terms with? This is my numerator. What can I replace sine squared plus cosine squared with? 1. So this becomes 1 plus, check it out, cosine theta, all of which the denominator is going to be sine theta times 1 plus cosine theta. And isn't that fantastic? Because what cancels? This whole quantity cancels here. What does that leave me with? 1 over sine theta, which is, by definition, cosecant theta. There's a lot of hints in what's on the other side as to what you should do when you're working with one side.